In this video, we will be looking at inequalities, both in the form of polynomials and also rational functions. We'll be taking the ideas we've been working on over the past week for graphing and then figuring out where functions are above or below the x-axis, greater than or less than or to 0. Inequalities that are based on a polynomial will have a polynomial and then a greater than or less than symbol, or we could have a greater than or equal, less than or equal sign. So here are some examples. When we're going to solve something like this, we want to look at the underlying equation that is associated with it. So by looking at, in this case, the quadratic x squared minus 4x minus 5, we can get a graph of that parabola. And the original problem is asking us, where are the places that this graph is greater than or equal to 0, right? Meaning, where is it above the x-axis? And we can see these two areas in blue that are above the x-axis. Looking down at the solution, the solution matches the graph. It's anything from negative infinity up to negative 1. Negative 1 is the intercept point that we're getting, right? The x-intercept. And then also from positive 5 to positive infinity, that relates to the other x-intercept. The area in the middle, which we've removed, is below the x-axis, and so it doesn't meet the criteria that we're looking for in the original problem. Now, by looking at a graph, it's sort of easy to see what the solution is. The way that we solve this algebraically is by breaking the number line up based on the x-intercepts. We're breaking the graph into 3 different sections. The first section goes to the first x-intercept, right, from negative infinity to negative 1. Sorry. The second section goes from negative 1 to 5. And then the third section goes from 5 to positive infinity. Typically what we do is a strategy of picking a test point in each of those particular regions. I can pick any point I want that for this first interval that is in between negative infinity and negative 1, and so I choose negative 2. I plug that into the original equation, and all I want to know is that output value, is the y value positive or negative? If it's positive, that means that everything within that same region will be positive, in this case above the x-axis. I'll do that for each of the 3 intervals, and I get this idea down at the bottom, the last line, of what the structure of the graph looks like, where it's above and below the x and y intercepts, and then in this case, where the function is actually positive, which is answering the original question, where is this graph greater than 0? Here are just the general steps to solving a polynomial inequality. We'll first set the equation equal to 0 so that we can figure out where the x-intercepts are. And then we'll break that, the whole number line up, or the whole x-axis up, into intervals that have their endpoints at the x-intercepts. And then we'll test points in each of those regions to determine where the graph satisfies the original inequality. If we have something that has greater than or equal, less than or equal, we include the endpoints, so we'll use a square bracket on our final solutions. Here's another example of a cubic. So the first thing that we do is think about what's happening with the graph if we set it equal to 0. X cubed minus x equals 0. The factored version we can see is x times x plus 1 times x minus 1. And so there are 3 places where we're getting zeros. They're at 0, at negative 1, and at positive 1. So what we've done is we've broken the number line up into sections with each of those zeros or x-intercepts as the barriers or the boundary points. So I'm taking the whole number line like this and saying, okay, I'm going to go to negative 1 for my first interval, then from negative 1 to 0 for my second interval, 0 to 1 for the third, and then 1 to infinity for the fourth. You can see that here are the intervals all set up. And then I pick a point, something, any point that I want, any x value that's somewhere in that particular interval. For this first example, I chose negative 2. I plug negative 2 into the original equation, and I end up getting a negative number. That corresponds to the fact that in this region, the graph is below the x-axis. When I pick a number that is in between negative 1 and 0, negative 0.5 in this case, I get that the graph is positive. That means that the graph is above the x-axis in that particular interval. And taking this last line of the table, I can say, if I just look at this number line that I've drawn here on the right, I can say the graph is going to be below down here because it's negative here. It's going to be above because it's positive here. Negative in this region and positive in this region. This gives me an idea of what's happening with the graph, right? Because it's got to be above and below the x-axis in certain areas. The answer to the original problem that they're asking, they wanted to know when this is greater than 0, and that happens in this region and then also in this region. And that's reflected in our answer down here. We've got it written in interval notation first, and then in set notation second. Hang on a second. I was there for a second because I was missing a slide. So the next example that I'm going to do is to solve this inequality. And you can see that the way it's set up initially, we don't have 0 on one side. So, just before we get started, we'll just move things around to get it set up more like the ones you were looking at before. So we'll have 3x to the fourth minus 11x cubed plus 10x minus 4. We want that to be less than or equal to 0. We want to know where that's less than or equal to 0. Now, I think the easiest thing to do is to start by graphing this on Desmos to figure out where some of the zeros are. I have a graph here that I put together, and we can see that one of the zeros is at negative 1, and then one of the zeros, I think, ends up being at 2/3. Those are the rational zeros that we get. We could do this by hand by going through that rational zeros theorem, but it turns out that 2 of the zeros end up being at negative 1, 2/3. And then if we break this equation down, we get something that we need to use the quadratic formula for. And so the other 2 zeros end up being 2 plus the square root of 2 and 2 minus the square root of 2. Again, I'm just using the ideas that we had from the last section where we looked at factors of negative 4 versus factors of 3 and test values. But again, you can look at Desmos to see where some of the rational numbers are, and then you can use synthetic division to break this down into smaller, smaller polynomial that you can factor or use a quadratic formula. So I want to get a decimal version for these numbers because I need to break up the number line. This is approximately 0.66, right? 2 plus the square root of 2 is about 3.4. And then 2 minus the square root of 2 is about 0.59. So when I break the number line up to test the intervals, I'll have negative 1 first. Then we'll have this one. This is the 2 minus square root of 2, 0.59. Then we'll have, I know these aren't spaced evenly, but 0.66. This is 2/3. I'm just breaking this up so I have room to work. And then this one would be 3.4, which is the 2 plus the square root of 2. So next what I'll do is select values in each of the intervals. Maybe I choose x equals -2 here and x equals 0. This interval is pretty tight, so I'll choose something right in the middle. X equals 0.6, that'll work. And then here we can choose x equals 1. Oh, and then we've got to do x equals, let's say 4 here. So what I do again is I take these 5 numbers, I plug them into this version here, and all I'm trying to determine is, do I end up getting something positive or do I end up getting something negative overall? And so I've got a bunch of different sections. I can see the graph down here. What ends up happening is this part is positive. This part's also positive. This is negative. This is negative. It turns out, though, that this little part is positive. And looking at the graph, though, the one on the left, it's kind of hard to see. It looks like maybe the graph just hits the x-axis and bounces back off of it. But in fact, this is that part like just zoomed in. You can see that there's a little portion of the graph that it actually goes above the x-axis. So the original was asking us to look for things that were less than or equal to 0. And so that's going to end up being this region here, and then also this region here. So our solution is going to be anything between -1 and 2 minus the square root of 2. We include the endpoints because we have equality in our original equation. And then we'll go from 2/3 to 2 plus the square root of 2. All right, here are the steps to solving an equation that's a rational inequality. It's really following the same exact idea where we're going to try to find where there are breaks in the graph. The only difference in this case is we have this idea of, we call them critical values, and what they are related to is either the zeros, meaning x-intercepts, or any asymptotes. And that's where we have the graph possibly changing whether it's above or below the x-axis. So here's an example. Similar to the last one, we don't have all of the terms on one side, so we start by subtracting 1 from both sides to get 0 by itself. To find the critical values, first we'll think about where the asymptotes are. The asymptote is going to come from the denominator, and I can see that 2x minus 4, we don't want that to equal 0, so x cannot equal to 2. So this first critical value is coming from an asymptote. The second critical value, it comes from the zeros, or where the function crosses the x-axis. And in the form that it currently is, I can't tell because I don't have a single fraction. So what I need to do is modify this by adding these together. I'll change this to be that -1 to 2x minus 4 over 2x minus 4. Just multiplying by that denominator so that they are in common. And I can combine these now to be, let's see, they'll get -x. The negative sign is going to distribute, so that'll be a plus 5. So this is this version right here is the same as this. These are equal to one another, right? But I like this version that I have on the right because I can see what the zeros are. The x-intercept is going to be at 5, and that's where I'm getting this second value. So I take both of those numbers and I break the number line up with 2 and 5 as the breakpoints. Pick test points and plug them in, and I get where the graph is positive and negative. And in this case, it wants us to determine where the graph is negative, below the x-axis. And these are the two portions. Now you can see in our solution, we've only included the endpoint for 5, but not at 2. Why is that? Well, the function is allowed to equal 0, right? We know that from our original. And so the 5 came from the x-intercept, right? From the zeros of the numerator. But the 2 came from an asymptote. And if we think about the domain of this function, 2 is not included in the domain. So we're not allowed to have 2 be one of the places where the function is actually equal. So when we think about inequalities that have an equal sign in them, we can include the zeros. You can see that happens here. But because there's an asymptote sitting right here, right, looks like that. The other part of the graph that's below the x-axis, it's this entire thing over here, but it doesn't include the number 2. All right, thank you for watching. Have a great day.